Okay, this lecture is like the beginning of the second half of this course, because up to now we paid a lot of attention to rectangular matrices. Now concentrating on square matrices. So we've got two big topics: the determinant of a square matrix. So this is the first lecture in that new chapter on determinants. And the big reason we need the determinants is for the eigenvalues. So this is really determinants and eigenvalues, the next big chunk of 1806. Okay, so the determinant is a number associated with every square matrix. So every square matrix has this number associated with it called its determinant. I'll often write it as DETA, or often also I'll write it as A with vertical bars. So that's going to mean the determinant of the matrix. That's going to mean this one, like, magic number. Well, one number can't tell you what the whole matrix was. But this one number just packs in as much information as possible into a single number. And of course, the one fact that you've seen before, and we have to see it again, is the matrix is invertible when the determinant is not 0. The matrix is singular when the determinant is 0. So that's the determinant will be a test for invertibility. But the determinant's got a lot more to it than that. So let me start. Okay, now the question is how to start. Do I give you a big formula for the determinant all in one gulp? I don't think so. That big formula has got too much packed in it. I would rather start with 3 properties of the determinant. Three properties that it has. And let me tell you property 1. The determinant of the identity is 1. Okay. I wish the other 2 properties were as easy to tell you as that. But actually, the second property is pretty straightforward, too. And then once we get the third, we will actually have the determinant. Those 3 properties define the determinant, and then we can figure out, well, what is the determinant? What's a formula for it? Okay, can I tell you the second property? That just like scales the determinant so that the identity matrix has determinant 1. Now, the second property is, what happens if you exchange 2 rows of a matrix? What happens to the determinant? So property 2 is exchange rows, reverse the sign of the determinant. A lot of plus and minus signs. I even wrote here plus and minus signs, because this is like that's what you have to pay attention to in the formulas and properties of determinants. So that you see what I mean by a property here. I haven't yet told you what the determinant is, but whatever it is, if I exchange 2 rows to get a different matrix, that reverses the sign of the determinant. And so now, actually, what matrices do we now know the determinant of? From 1 and 2, I now know the determinant. Well, I certainly know the determinant of the identity matrix. And now I know the determinant of every other matrix that comes from row exchanges, from the identity still. So what matrices have I got at this point? The permutations, right. At this point, I know every permutation matrix. So now I'm saying the determinant of a permutation matrix is 1 or minus 1. 1 or minus 1. Depending whether the number of exchanges was even or the number of exchanges was odd. So this is the determinant of a permutation. Now, P is back to standing for permutation. Okay. So if I could carry on this board, I could like do the 2 by 2s. So property 1 tells me that this 2 by 2 matrix, I better write vertical bars, not brackets, for that determinant. Property 1 said, in the 2 by 2 case, that this matrix has determinant 1. Property 2 tells me that this matrix has determinant, what? Negative 1. This is like 2 by 2. And now I finally want to get, well, ultimately I want to get to the formula that we all know. Let me put that way over here, that the determinant of a general 2 by 2 is AD minus BC. Okay. I'm going to leave that up like as the 2 by 2 case that we already know, so that every property I can like check that it's correct for 2 by 2s. But the whole point of these properties is that they're going to give me a formula for n by n. That's the whole point. They're going to give me this number that's a test for invertibility and other great properties for any size matrix. Okay, now you see I'm like slowing down because property 3 is the key property. Property 3 is the key property, and can I somehow describe it? Maybe I'll separate it into 3a and 3b. Property 3a says that if I multiply one of the rows, say the first row, by a number t, I'm going to erase that. That's like what I'm headed for, but I'm not there yet. That's the one we know, and you'll see that it's checked out by each property. Okay, now so this is for any matrix. For any matrix, if I multiply one row by t and leave the other row or other n minus 1 rows alone, what happens to the determinant? The factor t comes out. It's t times this determinant. That's not hard. I shouldn't have made a big deal out of property 3a. And 3b is that I'm always keeping this second row the same, or the last n minus 1 rows are all staying the same. I'm just looking inside the first row, and if I have an a plus a prime there, and a b plus b prime there, sorry, I didn't, why don't I use an eraser to do it right? B plus b prime there. Do you see what I'm doing? This property and this property are about linear combinations of the first row only, leaving the other rows unchanged. They'll copy along. Then I get the sum. This breaks up into the sum of this determinant and this one. If I'm putting up formulas, maybe I can try to say it in words. The determinant is a linear function. It behaves like a linear function of the first row if all the other rows stay the same. I am not saying that let me emphasize, I am not saying that the determinant of a plus b is determinant of A plus determinant of B. I am not saying that. How do I get it onto tape that I'm not saying that? You see, this would allow all the rows, A to have a bunch of rows, B to have a bunch of rows. That's not the linearity I'm after. I'm only after linearity in each row. Linear for each row. Well, you may say, I only talked about the first row. But I claim it's also linear in the second row. If I had this, but not, I can't have a combination in both first and second row. If I had a combination in the second row, then I could use rule 2 to put it up in the first row, use my property, and then use rule 2 again to put it back. So each row is okay, not only the first row, but each row separately. Okay, those are the 3 properties. And from those properties, so that's properties 1, 2, 3. From those, I want to learn a lot more about the determinant. Let me take an example. What would I like to learn? I would like to learn that, so here's a property 4. Let me use the same numbering as here. Property 4 is if 2 rows are equal, the determinant is 0. Okay, so property 4. 2 equal rows lead to determinant equals 0. Right. Now, of course, I can, in the 2 by 2 case, I can check, sure, the determinant of AB comes out 0. But I want to see why it's true for n by n. Suppose row 1 equals row 3 for a 7 by 7 matrix. So 2 rows are the same in a big matrix. And all I have to work with is these properties. The exchange property, which flips the sign, and the linearity property, which works in each row separately. Okay. Can you see the reason? How do I get this one out of properties 1, 2, 3? Because that's all I have to work with. Everything has to come from properties 1, 2, 3. Okay, so suppose I have a matrix, and 2 rows are equal. How do I see that its determinant has to be 0 from these properties? I do an exchange. Property 2 is just set up for this. Use property 2. Use exchange rows. Exchange those rows. And I get the same matrix. Of course, because those rows were equal. So the determinant didn't change. But on the other hand, property 2 says that the sign did change. So I have a determinant whose sign doesn't change and does change. And the only possibility then is that the determinant is 0. You see the reasoning there? Straightforward. Property 2 just told us, hey, if we've got 2 equal rows, we've got a 0 determinant. And of course, in our minds, that matches the fact that if I have 2 equal rows, the matrix isn't invertible. If I have 2 equal rows, I know that the rank is less than n. Okay, ready for property 5. Now, property 5 you'll recognize as a key. It says that the elimination step that I'm always doing, subtract some multiple L times row 1 from another row, row K, let's say. You remember why I did that. In elimination, I'm always choosing this multiplier so as to produce 0 in that position. Or row I from row K. Maybe I should just make very clear that there's nothing special about row 1 here. Okay, so that, you can see why I want that one. Because that will allow me to start with this full matrix, whose determinant I don't know, and I can do elimination and clean it out. I can get zeros below the diagonal by these elimination steps, and the point is that the determinant doesn't change. So all those steps of elimination are okay, not changing the determinant. In our language in the early chapter, the determinant of A is going to be the same as the determinant of U, the upper triangular one, that just has the pivots on the diagonal. That's why we'll want this property. Okay, do you see where that property is coming from? Let me do the 2 by 2 case. Let me do the 2 by 2 case here. So I'll keep property 5 going along. So what am I doing? I'm going to have AB, CD, but I'm going to subtract L times the first row from the second row. And that's the determinant. And of course, I can multiply that out and figure out, sure enough, AD minus BC is there. And this minus ALB plus ALB cancels out. But I just cheated, right? I've got to use the property. So what property? Well, of course, this is I'm keeping the first row the same. And the second row has a C and a D. And then there's the determinant of the A and the B, and the minus LA, and the minus LB. So what property was that? 3B. I kept one row the same, and I had a combination in the other row, and I just separated it out. Okay. So that's property 3. This is by number 3. 3B, if you like. Okay, now use 3A. How do you use 3A? Which says I can factor out an L. I can factor out a minus L here. I can factor a minus L out from this row, no problem. That was 3A. So now I've used property 3, and now I'm ready for the kill. Property 4 says that this determinant is 0. Has 2 equal rows. Do you see how that would always work? I subtract off a multiple of one row from another one. It gives me a combination in row K of the old row and L times this copy of a higher row. And then, since I have 2 equal rows, that's 0. So the determinant after elimination is the same as before. Good. Okay. Now, let's see. If I rescue my glasses, I can see what's property 6. Oh, 6 is easy. Plenty of space. Row of zeros leads to determinant of A equals 0. A complete row of zeros. So I'm again, this is like something that I'll use in the singular case. Actually, you can look ahead to why I need these properties. So I'm going to use property 5, the elimination, use this stuff to say that this determinant is the same as that determinant, and I'll produce a 0 there. But what if I also produce a 0 there? What if elimination gives a row of zeros? Then that used to be my test for singular, not invertible, rank less than n. And now I'm seeing it also gives determinant 0. How do I get that one from the previous properties? Because this is not a new law. This has got to come from the old one. So what shall I do? Yeah, that's brilliant. Use 3a with t equals 0. Right. So I have this 0, 0 CD, and I'm trying to show that that determinant is 0. Okay. So, but 0 is the same as 5. Can I take t equal 5? Just to, like, pin it down? I'll multiply this row by 5. 5, well, then 5 of this should, if there's a factor 5 in that, you see what? So this is property 3a with taking t as 5. If I multiply a row by 5, out comes a 5. So why the heck am I doing this? Oh, because that's still 0, 0, right? So that's this determinant equals 5 times this determinant. And the determinant has to be 0. I think I didn't do that the very best way. You had the idea better. Multiply, take t equals 0. Was that your idea? Yeah, better. Take t equals 0 in rule 3b. If t is 0 in rule 3b, can I bring the camera back to rule 3b? Sorry. If t is 0, then I have a 0, 0 there, and the determinant is 0. Okay. One way or another, a row of zeros means 0 determinant. Okay. Now I have to get serious. The next properties are the ones that we're building up to. Okay. So I can do elimination. I can reduce to a triangular matrix. And now what's the determinant of that triangular matrix? Suppose all right, rule 7. So suppose my matrix is now triangular. So it's got, shall I even give these the names of the pivots, D1, D2 to Dn? And stuff is up here. I don't know what that is. But what I do know is this is all 0. That's all 0. And I would like to know the determinant. Because elimination will get me to this. So once I'm here, what's the determinant then? Let me use an eraser to get that vertical bar again, so that I'm taking the determinant of u. So what is the determinant of an upper triangular matrix? Do you know the answer? It's just the product of the d's. These things that I don't even put in letters for, because they don't matter. The determinant is d1 times d2 times dn. If I have a triangular matrix, then the diagonal is all I have to look at. And that's telling us then. We now have the way that MATLAB, any reasonable software, would compute a determinant. If I have a matrix of size 100, the way I would actually compute its determinant would be elimination, make it triangular, multiply the pivots together. The product of the pivots. Product of pivots. Now there's always in determinants a plus or a minus sign to remember. Where does that come into this rule? Could the determinant be minus the product of the pivots? The determinant is d1, d2 to dn, no doubt about that. But to get to this triangular form, we may have had to do a row exchange. So it's the product of the pivots if there were no row exchanges. If SLU code, the simple LU code, just square LU went right through. If we had to do some row exchanges, then we've got to watch plus or minus. Okay, but this law is simply that. Okay, how do I prove that? Let's see. Let me suppose the D's are not 0. The pivots are not 0. And tell me, how do I show that none of this upper stuff makes any difference? How do I get zeros there? By elimination, right? I just multiply this row by the right number, subtract from that row, kills that. I multiply this row by the right number, kills that. By the right number, kills that. I can kill every one of these off-diagonal terms, no problem, and I'm just left with the diagonal. Well, strictly speaking, I still have to figure out why is, for a diagonal matrix now, why is that the right determinant? I mean, we sure hope it is, but why? I have to go back to properties 1, 2, 3. Why is, now that the matrix is suddenly diagonal, how do I know that the determinant is just the product of those diagonal entries? Well, what am I going to use? I'm going to use property 3a, is that right? I'll factor this. I'll factor that d1 out and have 1 in the first row will be that. And then I'll factor out the d2. Can I put the d2 here? And the second row will look like that, and so on. So I factored out all the d's, and what am I left with? The identity. And what rule do I finally get to use? Rule 1. Finally, this is the point where Rule 1 finally chips in and says that that determinant is 1, so it's the product of the d's. So this was rules 5 to do elimination, 3a to factor out the d's, and our best friend, Rule 1. And possibly Rule 2, the exchanges may have been needed also. Okay. Now, I guess I have to consider also the case if some d is 0. Because I was assuming I could use the d's to clean out and make it diagonal. But what if one of those diagonal entries is 0? Well, then with elimination, we know that we can get a row of zeros. And for a row of zeros, I'm using Rule 6. The determinant is 0, and that's right. So I can check the singular case. In fact, I can now get to the key point, that determinant of A is 0 exactly when A is singular. And otherwise, it's not 0. So that the determinant is a fair test for invertibility or non-invertibility. Okay. So I must be close to that because I can take any matrix and get there. Did I have anything to say? The proof starts by saying, by elimination, go from A to U. Oh, yeah. Actually, looks to me like I haven't said anything brand new here. That really, I've got this. Because let's just remember the reasoning. By elimination, I can go from the original A to U. Well, okay. Now, suppose the matrix is singular. Okay. If the matrix is singular, what happens? Then by elimination, I get a row of zeros. And therefore, the determinant is 0. And if the matrix is not singular, I don't get 0. So maybe, do you want me to put this like in two parts, the determinant of A is not 0 when A is invertible. Because I've already, in Chapter 2, we figured out when is the matrix invertible. It's invertible when elimination produces a full set of pivots. And we know the determinant is the product of those non-zero numbers. So those are the two cases. If it's singular, I go to a row of zeros. If it's invertible, I go to U, and then to the diagonal D, and then to D1, D2, up to Dn as the formula. So we have a formula now. We have a formula for the determinant, and it's actually a very much more practical formula than the AD minus BC formula. Is it correct? Maybe you should let's just check that. 2 by 2. What are the pivots of a 2 by 2 matrix? What does elimination do with that 2 by 2 matrix? There's the first pivot, fine. What's the second pivot? We subtract, so I'm putting it in its upper triangular form. My multiplier is C over A, right? I multiply that row by C over A, and I subtract to get that 0. And here I have D minus C over A times B. That's the elimination on a 2 by 2. So I've finally discovered that the determinant of this matrix, I've got it from the properties, not by knowing the answer from last year, that the determinant of this 2 by 2 is the product of A times that. And of course, when I multiply A by that, the product of that and that is AD minus the A's cancel BC. So that's great, provided A isn't 0. If A was 0, that step wasn't allowed. 0 wasn't a pivot. So that's what I've covered all the bases. I have to, if A is 0, then I have to do the exchange. And if the exchange doesn't work, it's because A is singular. Okay. Those are the direct properties of the determinant. And now, finally, I've got two more, 9 and 10. And that's, I think you can like, the ones we've got here are totally connected with our elimination process and whether pivots are available and whether we get a row of zeros. I think all that you can swallow in one shot. Let me tell you properties 9 and 10. They're quick to write down. They're very, very useful. So I'll just write them down and use them. Property 9 says that the determinant of a product, if I multiply two matrices, so if I multiply two matrices A and B, that the determinant of the product is determinant of A times determinant of B. And for me, that one is like, that's a very valuable property. And it's sort of like partly coming out of the blue because we haven't been multiplying matrices. And here suddenly, this determinant has this multiplying property. Remember, it didn't have the linear property. It didn't have the adding property. The determinant of A plus B is not the sum of the determinants. But the determinant of A times B is the product of it, is the product of it. Okay. So for example, what's the determinant of A inverse? Using that property 9. Let me put that under here because the camera is happier if it can focus on both at once. So let me put it underneath. The determinant of A inverse, because I won't, property 10 will come in that space. What does this tell me about A inverse, its determinant? Okay, well, what do I know about A inverse? I know that A inverse times A is I. So what am I going to do? I'm going to take determinants of both sides. The determinant of I is 1. And what's the determinant of A inverse A? That's a product of two matrices, A and B. So it's the product of the determinant. So what am I learning? I'm learning that the determinant of A inverse times the determinant of A is the determinant of I. That's this 1. Again, I happily use property 1. Okay, so that tells me that the determinant of A inverse is 1 over, here's my conclusion, is 1 over the determinant of A. I guess I always try to think, well, do we know some cases of that? Of course we know it's right already if A is diagonal. If A is a diagonal matrix, then its determinant is just the product of those numbers. So if A is, for example, 2, 3, then we know that A inverse is 1/2, 1/3. And sure enough, that has determinant 6, and that has determinant 1/6. And our rule checks. So somehow this property has to, somehow the proof of that property, if we can boil it down to diagonal matrices, then we can read it off. Whether it's A and A inverse or two different diagonal matrices, A and B. For diagonal, so what am I saying? I'm saying for diagonal matrices, check. But we'd have to do elimination steps. We'd have to patiently do the argument if we want to use these previous properties to get it for other matrices. It also tells me just let's see what else it's telling me. What's the determinant of A squared? If I take a matrix and square it, then the determinant just got squared, right? The determinant of A squared is the determinant of A times the determinant of A. So if I square the matrix, I square the determinant. If I double the matrix, what do I do to the determinant? Think about that. If I double the matrix, so the determinant of A, so I'm writing down like facts that follow. The determinant of A squared is the determinant of A all squared. The determinant of 2A is what? That's A plus A. But wait, I don't want the answer 2 determinant of A here. That's wrong. It's not 2 determinant of A. What is it? What's the number that I have to multiply determinant of A by if I double the whole matrix? If I double every entry in the matrix, what happens to the determinant? Suppose it's an n by n matrix. 2 to the n. Right. 2 to the nth. Now, why is it 2 to the nth and not just 2? So why is it 2 to the nth? because I'm factoring out 2 from every row. There's a factor, this has a factor 2 in every row. So I can factor 2 out of the first row. I factor a different 2 out of the second row, a different 2 out of the nth row. So I've got all those 2's coming out. So it's like volume, really, and that's one of the great applications of determinant. If I have a box and I double all the sides, I multiply the volume by 2 to the nth. If it's a box in 3 dimensions, I've multiplied the volume by 8. And this is rule 3a here. This is rule 9. And notice the way this rule sort of checks out with the singular, non-singular stuff. That if A is invertible, what does that mean about its determinant? It's not 0. And therefore, this makes sense. The case when determinant of A is 0, that's the case where my formula doesn't work anymore. If determinant of A is 0, this is ridiculous, and that's ridiculous. A inverse doesn't exist, and 1 over 0 doesn't make sense. OK. So don't miss this property. It's sort of like amazing that it can. And the 10th property is equally simple to state, that the determinant of A transpose equals the determinant of A. And of course, let's just check it on the A, B, C, D guy. We could check that, sure enough, that's A, B, C, D. It works. It's AD minus BC. It's AD minus BC, sure enough. So that transposing did not change the determinant. But what it does change is, what it does is it lists. So I've been working with rows. If a row is all zeros, the determinant is 0. But now, with Rule 10, I know what to do if a column is all 0. If a column is all 0, what's the determinant? 0 again. So like all those properties about rows, exchanging 2 rows reverses the sign. Now exchanging 2 columns reverses the sign. Because I can always, if I want to see why, I can transpose. Those columns become rows. I do the exchange. I transpose back. And I've done a column operation. So in conclusion, there was nothing special about row 1, because I could exchange rows. And now there's nothing special about rows that isn't equally true for columns, because this is the same. OK. And again, maybe I won't. Oh, let's see. Maybe it's worth seeing a quick proof of this number 10. A quick proof of number 10. Let me take this is number 10. A transpose equals A. Determinant of A transpose equals determinant of A. That's what I should have said. OK. So let's just a typical matrix A, if I use elimination, is factors into LU. And the transpose is U transpose L transpose. This is to prove. So this is proof number 10 using, well, I don't know which ones I'll use, so I'll put them all in, 1 to 9. OK. I'm going to prove number 10 by using 1 to 9. I won't cover every case, but I'll cover almost every case. So in almost every case, A can factor into LU, And A transpose can factor into that. Now what do I do next? So I want to prove that these are the same. I see a product here. So I use Rule 9. So now what I want to prove is, now I know that this is LU, this is U transpose, and L transpose. Now, just for practice, what are all those determinants? So this is prove this, prove this, prove this, and now I'm ready to do it. What's the determinant of L? You remember what L is? It's this lower triangular matrix with ones on the diagonal. So what is the determinant of that guy? It's 1. Anytime I have this triangular matrix, I can get rid of all the non-zeros down to the diagonal case. The determinant of L is 1. How about the determinant of L transpose? That's triangular also, right? Still got those ones on the diagonal. It's just the non-zeros flipped to the other side of the diagonal, but they didn't matter anyway. That's my proof, really. Then once I've got triangular matrices, L and L transpose, or U and U transpose, when they're triangular, I'm down to the product of the diagonal, and if I transpose, who cares? Okay, so that's not, I didn't put in every comma and cross every T in that proof, but that's really the proof. That's the concrete proof that get down to triangular matrices and then get down to diagonal matrices. Okay, one more comment, which I have to make, because all math professors watching this will be waiting for it. Okay, so they had to wait until the last minute. Way back in property 2, I said that if you do a row exchange, the determinant changes sign. So if I do 7 row exchanges, the determinant changes sign. But would it be possible to produce the same matrix with 7 row exchanges and with 10 row exchanges? If that were possible, that would be a bad thing, right? If I could, why would it be bad? My whole lecture would die, right? Because Rule 2 said that if you do 7 row exchanges, then the sign of the determinant reverses. But if you do 10 row exchanges, the sign of the determinant stays the same, because -1 10 times is +1. Okay, so there's a hidden fact here, that every permutation, the permutations are either odd or even. I could get the permutation with 7 row exchanges, then I could probably get it with 21 or 23 or 101, if it's an odd one, or an even number of permutations. So, but that's the key fact that this takes another little algebraic trick to see. And that means that the determinant is well defined by properties 1, 2, 3, and it's got properties 4 to 10. Okay, that's today, and I'll try to get the homework for next Wednesday onto the web this afternoon. Thank you.